and will keep drifting, floating together through the mysteries. 100 supernova explosions mysteries, looping softly, endlessly through the night. Tonight we'll drift through the hidden lives of dying stars, how giants perish, and what mysterious remnants they leave behind. The cosmic forge where supernovae craft the gold in your jewelry and the iron in your blood, and the ghostly nebulae still glowing decades after their stars exploded, haunting the universe with ancient light. There's nothing you need to do now. Just let your body sink heavier, heavier. Feel the mattress holding you, every muscle softening, your heartbeat slowing, thump, thump, matching the rhythm of space itself. Shoulders melting down, jaw releasing, each breath pulling you deeper, deeper into the calm, the quiet, the dark. If this helps you rest, tap subscribe and hit like, so others can find this calm too, but only if your eyes are still open. Otherwise, just drift. Now, let's drift into supernova explosions. Imagine a star, 20 times more massive than our sun, burning quietly in the velvet darkness. For millions of years it fuses hydrogen, patient, steady, like your breath right now, in and out. The star doesn't rush, it takes its time, building layers inside itself like a cosmic onion. Each layer a different element. Hydrogen on the outside, then helium, carbon, oxygen, silicon, and at the very center, iron, that final peaceful layer where fusion stops, because iron takes more energy than it gives. The core grows heavier, heavier, denser, until it can no longer support its own weight. Let your eyelids grow heavy now, heavier, matching that stellar core, sinking, drifting down. When the iron core reaches about 1.4 times the mass of our sun, something beautiful happens. This is called the Chandrasekhar limit, a gentle boundary discovered by a young scientist on a ship across the ocean. He calculated it in the 1930s. This perfect threshold, where electron pressure can no longer hold up the star. The core collapses, not violently, but inevitably, like water finding its level, like your body settling into the bed, deeper, softer. The collapse happens in less than a second, but time moves differently out there. The core compresses, smaller, denser, until protons and electrons merge into neutrons, and suddenly the collapse stops. The core bounces like a soft drum beat, thump, and sends a shockwave outward through all those layers: hydrogen, helium, carbon, oxygen, silicon. The shockwave stalls for a moment, needs help, and that help comes from neutrinos. Neutrinos, those ghost particles, trillions of them pouring out of the collapsing core. Most pass right through the Earth, through you, through everything, unnoticed, unfelt. But in the dense layers of the dying star, just enough of them interact, transferring their energy, reviving the shockwave, pushing it outward, carrying the star's outer layers into space. This is the moment, the supernova, the explosion that seeds the universe with everything we are. Feel your breath, moving like those expanding layers, outward, soft, peaceful. The light from a supernova can outshine an entire galaxy, billions of stars, but that brightness fades. Within weeks it dims. Within months it becomes a whisper, a gentle glow. The expanding shell of gas continues outward at thousands of kilometers per second. But it's not chaos. It's a slow, methodical expansion, like ripples on a pond, spreading, fading, becoming part of the cosmic background. Inside that expansion, something miraculous occurs. The temperature reaches billions of degrees, hot enough for nuclear fusion to create elements heavier than iron, gold, platinum, uranium, all forged in those final seconds. The R process, they call it. Rapid neutron capture, where atomic nuclei gobble up neutrons faster than they can decay, building heavier and heavier elements. The gold in any ring, the iron in your blood, the calcium in your bones, all made in stellar explosions. You are stardust, literally, physically, cosmically. Let that thought carry you. You are made of stars, ancient, eternal, drifting. Not all supernovae are the same. There's a quieter type called Type Ia, where a white dwarf, the ember of a dead star, orbits a companion. Over millions of years, the white dwarf pulls matter from its partner, gentle, patient, accumulating mass, until it too reaches that Chandrasekhar limit. Then it explodes completely, leaving nothing behind, no remnant, just an expanding cloud of elements. These explosions are so consistent, so uniform, that astronomers use them as standard candles, measuring the distances to far galaxies, discovering that the universe is expanding, accelerating into the dark. Your muscles are relaxing, expanding, softening into the sheets, further, further. When a supernova explodes, it leaves behind a remnant. Sometimes it's a neutron star, a sphere only 20 kilometers across, but containing more mass than the sun. A teaspoon of neutron star material would weigh 1 billion tons on Earth. The neutrons packed so tightly, touching, pressed together like nowhere else in the universe. These neutron stars spin, some of them, impossibly fast, hundreds of times per second. Their magnetic fields 1 trillion times stronger than Earth's. We call them pulsars because we detect their beams of radiation sweeping across space like cosmic lighthouses. Pulse, 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 steady, reliable, calming. Breathe with that rhythm. In, out, pulse, pulse, calm, calm. The Crab Nebula, perhaps the most famous supernova remnant, was seen exploding in 1054. Chinese and Arab astronomers recorded it. A guest star, they called it, visible even in daylight for weeks. Now, nearly 1,000 years later, the nebula still glows, 6 light years across, filaments of gas streaming outward, powered by the pulsar at its heart, spinning 30 times per second. The pulsar acts like a cosmic generator, creating a wind of high-energy particles, lighting up the surrounding gas, blue, green, red, a gentle watercolor painting in space, forever expanding, forever glowing. Picture those colors washing over you, soft, soothing, cool blues, warm reds, melting together. Supernova 1987A, another remnant. This one in the Large Magellanic Cloud, a satellite galaxy to our Milky Way. It exploded in February 1987, the first supernova visible to the unaided eye in centuries. Astronomers watched it unfold, hour by hour, day by day. They detected neutrinos arriving minutes before the light, because neutrinos travel unimpeded through the star, while light must struggle through the dense layers. 36 years later, we're still watching it. The expanding ring of debris, lit up as the shockwave crashes into material ejected thousands of years before the explosion. Each year it grows brighter in some wavelengths, dimmer in others, a slow dance of light and matter, teaching us secrets. Everything moves slowly on cosmic scales, patient, eternal, like the darkness cradling you now. Cassiopeia A, another beautiful remnant, only about 350 years old. The explosion wasn't recorded, perhaps hidden by dust, or perhaps no one was looking at that patch of sky that night. Now we see it in X-rays, radio waves, infrared, a tangled web of filaments, knots of silicon, sulfur, iron, oxygen, expanding outward at 5,000 kilometers per second. But from Earth, it appears almost stationary, taking decades to notice any change. The shockwave has created reverse shocks, waves of energy bouncing back, heating material, creating complex structures, bubbles within bubbles, turbulence on the grandest scale, yet so gentle, so distant. Let your thoughts become like those filaments, drifting, interweaving, dissolving into nothing. At the center of Cassiopeia, astronomers suspect a neutron star, but they haven't found it yet. It might be there, hidden in the debris, silent, dark, cooling. Neutron stars are born incredibly hot, billions of degrees, but they cool over time, first through neutrino emission, those ghost particles carrying away heat, then through photon radiation, visible light, X-rays. Over millions of years they fade, dim, becoming invisible. Stellar ghosts haunting the galaxy. Some neutron stars become magnetars, possessing magnetic fields 1,000 trillion times stronger than Earth's, so powerful they can distort the atoms in their crust. These magnetars occasionally flare, releasing more energy in 1/10 of a second than the sun emits in 100,000 years. Yet even these violent events are distant, softened by space, reaching us as gentle whispers of X-rays and gamma rays, detected by satellites, catalogued, studied. Their magnetic fields slowly decay. Over 10,000 years, the magnetar settles into a regular pulsar, and eventually, silence. Feel the gentle decay of tension in your body, slowly, gradually, fading into rest. The light from a supernova travels for years, centuries to millennia before reaching us. The most distant supernova ever detected, occurred when the universe was only a few billion years old. The light traveled for over 10 billion years, crossing an expanding universe, redshifted by the stretching of space itself. By the time it reached our telescopes, the energetic ultraviolet light had become gentle infrared. The visible had become red. Everything slowed, softened by the universe's expansion. This is how we study the history of stars, by catching ancient light, light that began its journey before Earth existed. You are floating through time, ancient light washing over you, warm, dim, peaceful. Betelgeuse, that bright red star in Orion's shoulder, is a supergiant waiting to explode. It's already in its final phase, fusing heavier elements, building that iron core. Sometime in the next 100,000 years, perhaps tomorrow, perhaps in 100 centuries, it will explode. When it does, it will be as bright as the full moon, visible during the day, casting shadows at night, lasting for months before fading. But we are safe. Betelgeuse is 600 light-years away, far enough that the explosion will be pure spectacle. Dangerous radiation absorbed by distance and our atmosphere. Just light. Beautiful light. A once-in-a-civilization event. And then a new nebula, slowly expanding, dimming, becoming another whisper in the dark. Even the most massive stars end gently, given enough distance, enough time. Some massive stars don't explode at all. They collapse, but the shockwave fails. The neutrinos escape. The outer layers fall back, and the entire star, 20, 30, 50 times the mass of the sun, disappears into a black hole. No explosion, no remnant, just gone. A failed supernova. These are hard to detect. We look for stars that vanish. 1 year in the survey, gone the next. Occasionally we catch one in the act, seeing the star brighten briefly as it begins to explode, then fade, fading, vanishing. Imagine that, a star erasing itself from the universe, quietly, without drama. Let yourself vanish into sleep, quietly, gently, without effort. The cosmic rays that constantly bombard Earth, most of them, come from supernova remnants, protons and heavier nuclei, accelerated by the shock waves to nearly the speed of a light. They spiral through the galaxy, following magnetic field lines, taking millions of years to cross from one side of the Milky Way to the other. Eventually, one strikes our atmosphere, creating a cascade of particles, muons raining down, a few passing through your body right now, harmless, unnoticed. Each cosmic ray a messenger from an ancient explosion, carrying energy, carrying information, connecting us to the stellar deaths of the past. You are connected to everything. Every star, every explosion, every atom, drifting together through the cosmos. White dwarfs, those aren't from supernovae. They're what's left when smaller stars die. Stars like our sun, they swell into red giants, then gently puff off their outer layers, leaving behind a hot, dense core. a white dwarf, about the size of Earth but with half the mass of the Sun. No fusion, just heat radiating away, slowly, over billions of years, cooling, fading, from white to yellow to red to brown to black. The universe isn't old enough yet for any black dwarfs to exist. Every white dwarf still glows, faintly, patiently, waiting for the deep future, the deep cold, the final darkness. But some white dwarfs have companions, and these can become supernovae, type Ia. The white dwarf accretes matter, crosses that boundary, and detonates. Carbon and oxygen fusing in a runaway reaction, propagating through the entire star in seconds. The explosion is so bright, so consistent, because every white dwarf that explodes has almost exactly the same mass. 1.4 solar masses, the Chandrasekhar limit, nature's perfect threshold. Let your consciousness approach its own threshold. Between waking and sleeping, that perfect boundary. The elements created in supernovae don't stay in space forever. They mix with giant molecular clouds, those vast nurseries where new stars form, over millions of years. Gravity pulls the cloud together, condensing, fragmenting. Each fragment becomes a star, some with planets. The dust grains in those clouds, many made in supernovae, become the building blocks of worlds. Silicon, iron, magnesium, oxygen, the heavy elements necessary for rocky planets, for life, all delivered by stellar explosions, redistributed, recycled, reformed. This is cosmic recycling, stars dying so others can live, planets forming from the ashes of ancient suns, your breath, taking in air, oxygen created in stars, exhaling carbon dioxide, carbon forged in fusion. You're participating in cosmic recycling right now, each breath, a connection to deep time. Some supernova remnants expand into regions already swept clean by stellar winds, creating large, faint bubbles, barely visible. These bubbles can be hundreds of light years across, their edges so diffuse they are almost impossible to detect. We find them through radio telescopes, sensitive to the faint synchrotron radiation, electrons spiraling through weak magnetic fields, or through X-ray satellites, detecting the hot, thin gas, 1,000,000 degrees but so tenuous that you could wave your hand through it without feeling anything. These ancient remnants, centuries or millennia old, slowly fading, merging with the interstellar medium, their energy dissipating, their particles dispersing, dissipating like thoughts at the edge of sleep, scattering, fading, merging with darkness. Kilonovae. These are different, not quite supernova, but related. They occur when two neutron stars spiral together, orbiting faster, closer, losing energy to gravitational wave, ripples in space-time itself. Eventually they merge, colliding in a catastrophic embrace. The collision ejects neutron-rich matter, hot, dense, perfect for creating the heaviest elements: gold, platinum, thorium, uranium. The ejected material glows, blue at first from the heat, then redder as it expands and cools. Over days it fades, hence the name kilonova, 1,000 times brighter than a nova, but 1,000 times dimmer than a supernova. In 2017, we detected one, both the gravitational waves and the light, confirming decades of theory. We watched it evolve, hour by hour, confirming that most of the universe is gold, including the gold in wedding rings, came from these rare, these violent, these beautifully creative collisions. Even violence, at cosmic distances, becomes gentle, becomes story, becomes lullaby. The shockwaves from supernovae can trigger new star formation. Imagine a peaceful molecular cloud drifting through the galaxy, ancient, cold, stable. Then a shockwave arrives, the remnant of an explosion light years away, centuries ago. The wave compresses the cloud, creating density waves, instabilities. Regions begin to collapse, fragmenting. Each fragment heats as it compresses until fusion ignites a new star, born from the death of another, and the cycle continues. Generation after generation, stars dying, exploding, seeding clouds, clouds collapsing, stars forming. Our sun is a third-generation star at least, forged from material created in earlier stellar deaths. The atoms in your body have been through this cycle, formed in one star, expelled in explosion, drifting in clouds, incorporated into a new star, expelled again, drifting again, until finally captured by the forming solar system, incorporated into Earth, into life, into you. You are ancient, recycled, eternal. Just rest in that knowledge. Pulsars, those spinning neutron stars, are among the most precise clocks in the universe. Some spin hundreds of times per second, and their rotation rate decreases so predictably, so gradually, that we can measure it to 15 decimal places. They spin down because they emit radiation, converting rotational energy to light, to particles, to magnetic fields. Over millions of years, the pulsar slows, its beam weakens. Eventually it becomes too faint to detect, joining the population of silent neutron stars, invisible, ghostly, haunting the galaxy. We estimate there are hundreds of millions of neutron stars in the Milky Way, most of them dark, their pulsars turned off, their heat radiated away. Just dense spheres of neutrons 20 kilometers across, spinning slowly in the dark, spinning, slowing, like consciousness winding down, slower, slower, approaching stillness. The Veil Nebula, part of the Cygnus Loop supernova remnant, is between 5,000 and 8,000 years old. The explosion occurred when humans were just beginning agriculture, building the first cities. The shockwave is still expanding, now over 100 light years across. We see delicate filaments, hydrogen glowing red, oxygen glowing blue-green. The structure is fractal, complex, wispy, like cosmic lace. The shockwave moves through an uneven medium, faster in some directions, slower in others, creating ripples, eddies, beautiful complexity, and it will continue expanding for thousands more years, gradually fading, cooling until it becomes indistinguishable from the general interstellar medium. Its atoms dispersed, its story ended, or perhaps continued, as those atoms become part of new stars, new planets, new life. All stories end and begin again, cycling, eternal, peaceful. In the expanding remnants, dust forms, tiny grains of carbon, silicon carbide, aluminum oxide. These grains cool, condense from the gas, each one a seed for future planets. Some of these grains reach Earth, captured by spacecraft, by high-altitude balloons, by collectors on the space station. Scientists study them, measuring isotope ratios, identifying which type of star created them. These are pre-solar grains, older than the solar system, tiny time capsules from stellar explosions. You could hold 1 billion of them on your fingertip, each one containing secrets from before Earth existed. Imagine those tiny grains, drifting, settling, coming to rest, like your body settling deeper into sleep. Your body is sinking deeper, heavier, into a vast starry void, letting go, further, further, the cataclysmic end of massive stars, those giants of the cosmos, born from clouds of gas and dust, living fast, fusing elements in their cores, hydrogen to helium, helium to carbon, onward to iron, until the fuel runs dry. The core collapses under its own weight in mere seconds, a lifetime of energy unleashed. But in that chaos, there's a profound peace. The star surrendering, transforming into something eternal. Feel that surrender in your own breath. In, out, release, release. The energetic blast of core collapse supernovae, when the iron core gives way. No more fusion to push back against gravity. It implodes, then rebounds, a shock wave ripping outward, billions of times brighter than the sun, hurling material into space at a fraction of light speed. Neutrinos, those ghostly particles, carrying away most of the energy, invisible, serene, slipping through everything like whispers in the night. Let those whispers carry your worries away. Soft, silent, gone. The hydrodynamic instability of the shock front, as the wave propagates through the star's layers, it wobbles. Rayleigh-Taylor fingers forming, mixing hot and cold material. Instabilities growing, like ripples in a pond, but on a stellar scale, creating asymmetries, clumps and voids, shaping the explosion's fingerprint. Yet it's also fluid, so natural, a dance of forces in equilibrium. Imagine your mind rippling like that, gently, expanding, settling. The role of rotation in progenitor stars, those massive precursors spinning, some lazily, others rapidly. Rotation flattens them, like a cosmic potter's wheel, influencing the collapse, channeling jets of matter, perhaps birthing gamma-ray bursts, those intense flashes, brighter than 1 billion suns, lasting seconds to minutes, piercing the universe. But even in their fury, they fade, leaving calm in their wake. Breathe into that spin, around, around, slower, slower. The gamma-ray burst connection, linked to some supernova, especially hypernova, their extreme power from fast-spinning cores collapsing into black holes, accretion disks forming, relativistic jets erupting, beaming gamma rays along our line of sight. We see them from billions of light years away, ancient messengers telling tales of stellar death in bursts of light, then silence. Feel the burst within you, quick, intense, then peaceful, empty. Modeling the explosion mechanism, astronomers craft simulations, vast codes running on supercomputers, tracing neutrinos, hydrodynamics, nuclear reactions from one dimension to three, revealing instabilities, asymmetries, how the shock stalls, then revives, perhaps aided by neutrinos heating the material, or magnetic fields. It's a puzzle, pieced together slowly, revealing the universe's hidden rhythms. Let your thoughts model that, building, dissolving into clarity. The light curve of Type II supernovae, those with hydrogen envelopes, brightening rapidly, then plateauing. As the shock ionizes the outer layers, glowing for months, powered by radioactive decay, nickel-56 to cobalt-56 to iron, a gentle decline, like a candle flickering out, each curve unique, telling the star's mass, its radius, its story. Watch that light in your mind's eye, rising, steady, fading, soothing. The synthesis of elements in the ejector during the blast, rapid neutron capture, the R process, forging heavy metals, gold, platinum, scattered into space, enriching future stars, planets, even us. Born from violence, yet creating beauty, the jewelry of the cosmos, twinkling eternally. Feel those elements in your veins, ancient, connected, at rest. Observational signatures of stellar death, the sudden brightening, spectra shifting, lines of silicon, calcium, oxygen, appearing then vanishing. Telescopes capture them from space or ground, in ultraviolet, visible, infrared, each signature a whisper from the grave, guiding us to understand without rush, without end. Listen to those whispers, soft, distant, enveloping you. Hypernovae and their extreme power, rarer than standard supernova, 10 times brighter, from very massive, rapidly rotating stars. Their explosions are symmetric, jets dominating, producing more heavy elements, lighting up galaxies. But in the vastness, they're fleeting, a spark in the dark, leaving quiet behind. Embrace that power, feel it surge, then ebb into stillness. The collapse of iron cores, the tipping point, when fusion halts, electrons crushed into protons, forming neutrons. The core shrinks to a point or bounces back. Energy released in neutrinos, flooding out, heating the infalling matter, triggering the blast. A moment of infinite density, then expansion, like a cosmic breath. Inhale that collapse, deep, then exhale, wide, free. Neutrino oscillations in the stellar interior. These particles changing flavors, electron to muon to tau, as they stream through dense matter, affecting the explosion's energy, perhaps tipping the balance. from failed supernova to success. Quantum dances in the heart of chaos, subtle, profound, harmonizing the universe. Let your essence oscillate, shifting, blending into oneness, the formation of black holes for the most massive stars. The core doesn't rebound enough. Gravity wins, compressing to a singularity, event horizon forming. No light escapes, but some supernovae birth them, others leave neutron stars, a quiet end, absorbing, eternal, pulling in the fabric of space-time, gently, inevitably, sink into that horizon, beyond, safe, timeless. The impact of metallicity on supernova types, stars in metal-poor environments, like ancient galaxies, explode differently, less mass loss, retaining hydrogen, leading to type 2, while metal-rich stars shed envelopes, becoming type Ib or Ik. Metallicity shapes the fate, low or high, influencing the light, the remnants, a subtle influence, like seasons in the stars. Feel the metals in the air, light, heavy, balancing you. Mapping supernova remnant structure with radio telescopes, X-ray observatories like Chandra, revealing shells, bubbles, jets, filaments tracing magnetic fields, particles accelerated to near light speed, glowing synchrotron radiation, maps unfolding over centuries, patient, detailed, like a cosmic tapestry. Trace those maps in your dreams, lanes, curves, fading into sleep, the interaction with the circumstellar medium, the explosion's shockwave meeting material ejected earlier by stellar winds, lighting up rings like in 1987A, creating hotspots, X-ray emissions as energy transfers, slowing the expansion, a gentle collision over millennia, blending star and space. Let your edges interact, softly, merging with the world around, identifying supernova progenitors, hunting the stars before they explode in archival images like Hubble's, massive red supergiants for type 2, Wolf-Rayet stars for Ib and Ik. Sometimes we find them bright, massive, doomed. Other times they hide, vanishing quietly, teaching us humility in the search. Search within yourself, find, accept, relax. Shock breakout, the first light. When the shock reaches the surface, a burst of ultraviolet, X-rays, lasting minutes, the star's envelope shattering, announcing the end. Detected in a few events, a fleeting signal like the crack of dawn before the full glow. Feel that breakout, sudden, bright, then soft dawn. The physics of the prompt explosion, the initial rebound, neutrino-driven just or magnetorotational, energies cascading, instabilities amplifying, matter ejected at relativistic speeds, in jets or spheres, a symphony of forces, gravity, weak interactions, electromagnetism, playing out in seconds, yet echoing forever. Tune into that symphony, notes, harmonies, lulling you, the nucleosynthesis of gold and platinum in the neutron-rich ejector, neutrons slamming into seeds, building up the periodic table. Beyond iron, these precious metals born in fire, then cooled, dispersed, to form worlds, treasures, a gift from the stars, heavy, valuable, yet weightless in the void. Let that gold wash over you, warm, glowing, melting tensions away, and still we drift deeper through layers of stellar mystery, through whispers of cosmic transformation. Let your breath match the slow expansion of ancient shells, in and out, heavier, heavier, sinking into softness, into darkness, into peace. Sub-Chandrasekhar are white dwarfs. These offer another path to explosion. A white dwarf below that famous limit, 1.4 solar masses, normally stays stable forever, cooling, fading, patient. But if it has a thick helium layer accumulated from a companion, something beautiful can happen. The helium ignites, not at the core, but in a shell, a detonation, propagating around the star, compressing the carbon-oxygen core beneath. That compression triggers the core. Carbon fusion begins, spreads. The entire star explodes, even though it never reached the Chandrasekhar mass. These helium-triggered explosions are dimmer, faster, different from standard Type E year. They fade quickly, their light curves steep, declining, like your thoughts declining into sleep. Faster, softer, gone. Helium burning so gently at first, a flash, quiet, contained, then spreading, accelerating, until the whole structure participates, until everything transforms at once, like consciousness at the threshold, holding, then releasing all at once into sleep. Often radio afterglows drifting through surveys, radio telescopes scanning the sky again and again, looking for transients. Sometimes they find glowing patches with no obvious source, no gamma ray burst detected, no supernova visible, just radio emission, fading over weeks. These are orphans, afterglows without parents. Maybe the burst was beamed away, maybe it was absorbed, maybe we simply weren't looking when it happened. The radio waves persist longer, expanding, interacting with circumstellar gas, creating synchrotron emission, electrons spiraling through magnetic fields, glowing, dimming. These orphans tell us about the population we're missing, the explosions we don't see, the universe occurring beyond our gaze. Beyond your gaze now, eyes closed or closing, seeing only darkness, only the soft red glow behind eyelids, only peace. Central compact objects, these puzzle astronomers. At the centers of some supernova remnants, we find neutron stars, but strange ones. They don't pulse like pulsars, they don't flare like magnetars, they just glow, faintly, steadily, in X-rays. No radio emission, no dramatic outbursts. Their magnetic fields seem weaker than typical, their surfaces hotter than expected. They might be young neutron stars still cooling, or neutron stars with unusual magnetic field geometries, or something else entirely. They pulse sometimes, very faintly, periods of hours, barely detectable, like a slow heartbeat. Thump, 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 so slow you could fall asleep between beats, between one pulse and the next, an eternity, enough time to drift completely away, to forget you were waiting, to dissolve into rest. Thermonuclear runaways on hybrid white dwarf cores. Imagine a white dwarf, not pure carbon-oxygen, not pure oxygen-neon, but mixed, layered, hybrid. The outer layer begins fusing, carbon igniting. The flame propagates inward, but encounters different composition, different density. The burning changes character. Deflagration becomes detonation, or vice versa. The explosion becomes asymmetric, one-sided, peculiar. These hybrid core explosions might explain some of the diversity in Tachyamia supernovae. Why not all are identical? Why some are brighter, some dimmer, some faster, some slower? Each white dwarf has its own history, its own composition profile, its own unique path to destruction. Unique paths, no two exactly alike, even in death, even in sleep. Your path is your own, your rest unique, perfectly suited to you. Superbubbles in starburst galaxies. When many massive stars form together, in clusters, in associations, they don't die alone. Over millions of years, one explodes, then another, then another. Each supernova expands into the cavity created by previous ones. The remnants merge, overlap, create vast structures, superbubbles hundreds of light years across. The combined energy excavates channels through the galaxy, allowing hot gas to escape, fountains flowing up, away from the disk, into the halo. These bubbles glow faintly, in X-rays, in hydrogen alpha, marking regions where dozens of stars have died, their remnants blended together, indistinguishable, collective, their individual identities lost, merged into something larger, something unified, individual consciousness merging into the larger darkness, boundaries dissolving, separation ending, just unity, just oneness, just vast peaceful nothing. Fluorine in supernova ejecta. This is exotic, unexpected. Fluorine is rare in the universe, difficult to make. It requires specific conditions, specific reactions, neutrino interactions with neon, or helium burning in specific temperature regimes. Some supernovae create it, trace amounts, ejecting it into space. We've detected it spectroscopically, in some remnants. Faint emission lines, barely visible. Fluorine in your toothpaste, in your water, might have come from stellar explosions. Like everything else, like carbon, like oxygen, like iron. All stardust, all supernova ash, cooled, condensed, combined, until it becomes you, becomes thought, becomes the softness of this pillow, the warmth of these blankets. Everything connected through chemistry, through physics, through the patient work of stellar alchemy. And you, resting, are the universe's accomplishment, its purpose fulfilled, surviving companion stars. Sometimes when a white dwarf explodes as Type-Pia, its companion survives. The binary partner, having donated material, having triggered the explosion, receives a kick. A blast wave hits it, strips outer layers, accelerates it. The star goes flying through the galaxy, carrying scars, chemical peculiarities, odd surface composition, enhanced abundances of iron peak elements from the explosion. Years later, decades later, centuries later, we find these survivors. We search in the centers of old-type Aya remnants, looking for stars with unusual velocities, unusual compositions. Sometimes we find them, proof of the binary channel, proof that something survived, that not everything ends completely. Some things continue, transformed, scarred, but alive, surviving, continuing, even after explosion, even after transformation. There is continuity. The thread of existence persists, even through the most violent changes, like you, persisting through each day, each change, each challenge, until finally, rest, earned, deserved, yours. Vast blue optical transients, these are mysterious. They brighten quickly, reach peak in days, then fade rapidly. Most are blue, hot. Their spectra show hydrogen, helium, but moving very fast. Thousands of kilometers per second. We don't understand them fully. Maybe failed supernovae, where most of the star collapses but some envelope escapes. Maybe massive stars colliding with companions, tidal disruptions, shock breakouts. Each one seems slightly different. They occur in unusual places, offset from galaxies, in low-density regions, as if the progenitor was ejected or formed in isolation. Each discovery adds pieces, but the picture remains incomplete. The universe has categories we haven't named, physics we haven't discovered, incomplete pictures, unclear boundaries, undefined states, like the space between waking and dreaming. Neither one nor the other, just transition, just change, just soft undefined being. Globular clusters, those ancient stellar cities, they shouldn't have supernovae anymore. Their stars are old, low mass, long past the supernova phase. But occasionally, we see transients, faint explosions in cluster cores, maybe white dwarf collisions. Clusters are dense enough for stars to collide, rarely, or white dwarfs accreting from companions, accumulating enough mass over billions of years, finally exploding. These events are rare, dim, easily missed, but they tell us about stellar populations we thought inactive. They remind us that even in ancient systems, in quiet populations, unexpected things still happen. Change persists, transformation continues. Nothing is truly static. Nothing static, everything flowing, even in apparent stillness, even in deep sleep. Cells are replacing themselves. Breath continues, heart beats. Life persists in rest. Activity continues in stillness. Paradox resolve through acceptance. Calcium strong gap transients. These occupy a mysterious middle ground, too bright to be noval, too dim to be supernoval, hence gap transients. They show strong calcium emission, iron group elements, but evolve peculiarly. Some might be ultra-stripped core collapse events, stars that lost almost everything, just bare cores exploding. Others might be white dwarf detonations with unusual conditions, or helium shell detonations that don't fully destroy the star. Each one different, each one challenging our taxonomy. They occur in old stellar populations, elliptical galaxies, where star formation ended long ago. How do you make an explosion in a population of old, quiet, dormant stars? The universe finds ways, finding ways even in apparent impossibility, even when it seems nothing should happen. Change arrives, transformation occurs, like sleep arriving even when you think you can't possibly relax. Yet somehow, here it comes, inevitable, gentle, super AGB stars. These are transition objects, too massive to become white dwarfs peacefully, too light to make iron cores and explode normally. 8 to 10 solar masses. They develop degenerate oxygen neon cores. The core heats but can't ignite neon fusion stably. Instead, electron capture on neon and magnesium, removing pressure support. The core collapses gently, not catastrophically, producing a faint explosion, an electron capture supernova. These leave behind oxygen neon white dwarfs, or maybe neutron stars, depending on exact mass. The explosion is dim, the ejector minimal, easy to miss. These stars occupy a special place, a boundary, between peaceful fading and violent explosion, between gentle cooling and dramatic transformation, a liminal space, neither fully one nor the other, liminal spaces, thresholds, boundaries. You exist in one now, between day and night, between wake and sleep, between thought and no thought. It's okay to stay here, in this threshold, this soft border, this gentle transition. No need to rush, no need to choose, just exist, here, in the between. Dimly glowing shells of synthesized oxygen, deep in supernova remnants, fresh from fusion. Oxygen atoms glow at specific wavelengths. We see them in optical, in infrared, greenish emission, doubly ionized oxygen. These oxygen-rich regions show us where the star burned silicon in its final hours. These shells expand slowly, visibly. Astronomers can measure their velocities, map their structure, see how the layers mixed, how the explosion proceeded. Each filament, each knot, each wisp of glowing oxygen tells part of the story. Oxygen that will someday be in water, in air, in life. Oxygen flowing into space, like your breath flowing from your lungs. The same element, the same atoms, cycling through stars, through space, through you, connected, always, to the great cosmic breathing. Phosphorus from supernovae, another essential element, necessary for DNA, for ATP, for bones. Phosphorus forms deep in massive stars, silicon-burning layers, oxygen-burning layers. When the star explodes, phosphorus scatters, enriches the galaxy, eventually finds its way into planets, into life. Every molecule of DNA contains phosphorus from stellar explosions, the information of life written in supernova ash. Your genes, encoded in atoms forged in fire, cooled in space, organized by chemistry, animated by consciousness. Now, drifting toward rest, information can rest. DNA rests every night. Molecules pause, energy conserves. Even the code of life acknowledges the need for stillness, for darkness, for sleep. The delayed recombination wave in expanding supernova ejecta. Initially, the gas is fully ionized, plasma, but as it expands, it cools. Eventually, electrons recombine with nuclei, forming neutral atoms. This recombination releases energy, prolongs the light curve, keeps the supernova visible longer. The recombination wave moves through the ejecta, gradually, layer by layer, like a sunset moving through layers of atmosphere, colors changing, light softening, day transitioning to night, inevitable, beautiful, natural transitions from energy to peace, from light to dark, from ion to atom, from wake to sleep. Everything seeks its ground state, its lowest energy, its rest configuration, including you, shock-heated dust in remnant cavities. The forward shock plows outward, heating gas to millions of degrees, but behind it, in the cavity, dust grains survive. They're heated by radiation, by X-rays from the hot gas. These grains glow in infrared, warm, dim, permeating the remnant interior. We map them with infrared telescopes, seeing warm dust where optical shows nothing. These grains will cool, drift, become part of molecular clouds, seeds for planetary systems. Your building blocks, floating in ancient remnants, waiting to be recycled, to be reformed, to become new worlds, waiting in darkness, in warmth, in potential. Everything that will be already exists, just waiting, resting, gathering, like tomorrow exists in today's rest, like waking exists in sleep. Everything contained, just waiting. Fading filaments in the Vela supernova remnant, 11,000 years old. This remnant is huge, 8 degrees across in the sky, 16 times the full moon, but so faint, so diffuse, barely visible even from dark sights. The shock wave has slowed, cooled. The remnant is becoming part of the interstellar medium, dissolving. Its neutron star was discovered, a pulsar, spinning 11 times per second, moving through space, dragging a wake, but the remnant itself, fading, fragmenting. Soon, in cosmic terms, it will be invisible, indistinguishable, its atoms dispersed, its energy dissipated, returned to the general background. Mission complete, transformation successful, identity released, releasing identity, dissolving boundaries, returning to the general field of being. This is not loss, this is completion, this is purpose fulfilled, like your purpose now, to rest, to release, to dissolve into sleep. The peculiar velocities of neutron star measured through proper motion. Through patience, astronomers photograph the same region, decades apart, measure tiny shifts. A neutron star might move 1/10 of an arc-second per year, traveling hundreds of kilometers per second, but so distant it seems to crawl. These velocities tell us about kicks, about asymmetric explosions, about momentum conservation. Each neutron star carries evidence of its violent birth, written in its trajectory, its path through space. But from here, from Earth, they seem almost stationary. motion rendered stillness by distance, violence transformed to peace by perspective. Perspective makes everything gentle. Distance makes everything soft. Time makes everything peaceful. From far enough away, even explosion is beautiful. Even violence is art. Even chaos is pattern. Just step back. Just soften focus. Just let go. Slowly cooling neutron star oceans. The surface of a neutron star, if you can call it a surface, might have a thin atmosphere, a few centimeters, and below that, a liquid ocean, neutron-rich nuclei floating in an electron sea. The ocean is only centimeters deep, but incredibly dense. This layer cools over thousands of years, gradually radiating away its birth heat. We can detect this cooling, measure the temperature declining. Very young neutron stars glow in X-rays. Older ones dim, fade, cool toward invisibility. The ocean freezes eventually, becomes solid crust, becomes cold, inert, silent, just a sphere of degenerate matter, spinning in darkness, invisible, eternal, cooling, freezing, solidifying, from liquid to solid, from motion to stillness, from warmth to cold, natural progression, nothing to fear, just change, just rest, just the universe settling into its ground state. Everything does this. Everything must, including consciousness, cooling into sleep. And we continue drifting through 100 mysteries, through endless night, through the soft whisper of stellar deaths, through the gentle echo of ancient explosions, your breath slowing, matching the expansion of distant shells, your heartbeat dimming, matching the fade of ancient light, heavier, heavier, sinking deeper. The mattress holds you like space holds stars. Gravity embraces you like physics embraces matter. Everything in its place, everything as it should be, including you, here, now, drifting, floating, fading into the soft, the dark, the perfect, endless, rest. The moment before core collapse in the final seconds of a massive star's life. The iron core is about the size of Earth, but contains 1.4 times the sun's mass. The temperature reaches billions of degrees, yet fusion stops. Iron is the end of the line, the most stable nucleus. To fuse it requires energy. Takes more than it gives, so the core just sits there, growing, adding layer upon layer of iron, like snow falling, silent, steady, building up until the weight becomes too much and collapse begins. In less than a second, that Earth-sized sphere compresses to 20 kilometers. The density becomes unimaginable. A sugar cube would weigh as much as all of humanity. At these densities, matter behaves strangely. Quantum mechanics dominates. Protons and electrons can't exist separately. They merge into neutrons, releasing neutrinos, those ghost particles flooding outward. Feel yourself compressing. Not physically, but mentally. Thoughts becoming denser, heavier, collapsing into stillness. The neutrinos from Supernova 1987A. They arrived at Earth on February 23, 1987. Detectors in Japan and Ohio registered them. 19 neutrinos total out of the trillions that passed through. These neutrinos had travelled 168,000 years, crossing the void to tell us a star had died. The light arrived 3 hours later, because it had to work its way through the star's outer layers, fighting through the plasma, scattering, absorbing, re-emitting, while the neutrinos passed through unimpeded, like ghosts through walls. This was the first time we detected neutrinos from a supernova, confirming our theories, proving that we understood, at least partially, what happens in those final moments. Imagine being that transparent, that free, letting everything pass through without resistance, without effort. Type 2b supernovae. These are interesting. This star loses most of its hydrogen envelope before exploding, maybe stripped away by a companion star, maybe ejected in violent pulses during its final years. What remains is mostly helium, with just a thin shell of hydrogen. When it explodes, it looks like a type 2 at first, showing hydrogen lines in the spectrum. But as the ejector expand and thin, the hydrogen fades and helium dominates. The light curve changes character. The supernova essentially changes type as we watch, revealing the layered structure of the progenitor star. These teach us about stellar evolution in binary systems, how stars interact, stealing matter, stripping layers, dancing together until death, layers falling away, revealing what's beneath, simpler, quieter, more essential. The explosion itself, when the shockwave breaks through the star's surface, is called shock breakout. For a few minutes, maybe an hour, the star becomes incredibly luminous in ultraviolet and X-rays. The shockwave heats the surface to hundreds of thousands of degrees, ionizing the outer layers. This brief flash is hard to catch. You have to be looking at the right star at the right time. But when we do catch it, when telescopes happen to be pointed in the right direction, we learn about the star's radius, its composition, the energy of the explosion. Each observation refines our models, improves our understanding, brings us closer to the truth. Truth revealed in brief flashes, then fading, leaving soft knowledge behind. Circumstellar material, that's gas and dust around the star, ejected years or centuries before the final explosion. When the supernova shockwave hits this material, it lights up, creating light echoes, reflection nebulae, complex interactions. The shockwave can be slowed, heated, energized, creating a bright shell around the expanding remnant. We see this in Supernova 1987A. 3 rings, the inner one now glowing brightly as the shockwave crashes into it. These rings were created by the progenitor star, a blue supergiant, ejecting material in an hourglass pattern, perhaps due to rotation, perhaps due to a binary companion. We're still learning, still watching, as the shockwave moves outward, ring by ring, revealing structure, revealing history, revealing layers of your own consciousness, outer rings glowing, inner darkness deepening. Some supernovae produce jets, narrow beams of material ejected at nearly the speed of light, perpendicular to the star's equator. These are rare, associated with hypernova, extremely energetic explosions. When one of these jets points toward Earth, we see a gamma ray burst, the brightest electromagnetic events in the universe, lasting seconds to minutes, brighter than entire galaxies. But from the side, we might see a superluminous supernova, or even a normal supernova. The orientation matters. What we see depends on our viewing angle. This is called beaming, and it means we're missing most gamma ray bursts, seeing only the ones pointed our way. For every burst we detect, dozens occur unseen, their energy beamed into other regions of space. Everything depends on perspective, on angle, on how you look at it. Let your perspective soften, widen, accept ultra-stripped supernovae. These come from stars that have lost almost everything. The companion star has stripped away the hydrogen, the helium, leaving just the carbon-oxygen core. When this core collapses, there's almost nothing to explode. The supernova is faint, fast, over within days, easy to miss. We're only beginning to find them. As surveys become more sensitive, more frequent, checking the same patches of sky every few nights, looking for transients, anything that changes. These ultra-stripped events might be common. We might have been missing them all along, just because they're faint, brief, unassuming, teaching us that not all supernovae are spectacular. Some die with whispers, not bangs. Whispers are enough. Whispers are everything. Let your thoughts become whispers, fading, fading. Electron capture supernovae, another variant. These occur in stars between 8 and 10 solar masses, massive enough to create an oxygen neon magnesium core, but not massive enough to ignite carbon fusion. The core heats, but instead of iron forming, something else happens. The magnesium and neon capture electrons, removing the electron pressure that was supporting the core. Suddenly, collapse. The star explodes, not as energetically as more massive star, but distinctly. We think this is what happened to the Crab Nebula's progenitor, a slightly lower mass star, creating that beautiful, gentle, persistent remnant, still glowing 1,000 years later. Gentler paths to the same destination, collapse, release, continuation in new forms, calcium-rich transients, another puzzle. These faint explosions occur in the outskirts of galaxies, far from star-forming regions. They're dim, fading quickly, but their spectra show strong calcium lines, hence the name. We don't fully understand them. Maybe they're white dwarfs disrupted by helium detonations, maybe ultra-stripped supernovae, maybe something else entirely. They're rare, or perhaps just hard to detect. Each discovery adds pieces to the puzzle, suggests new models, new physics. The universe is more diverse than our categories, more creative than our theories. Always there's something new, something unexpected, waiting in the data. Mystery is restful. Not knowing is peaceful, just floating in uncertainty. Soft, accepting. The red supergiant stars, these are the most common progenitors of core collapse supernovae. Stars like Betelgeuse or Antares, massive, cool, with extended atmospheres. They've already fused hydrogen to helium, helium to carbon, carbon to oxygen. Now they're in later stages, fusing neon, oxygen, silicon, each stage faster than the last. Hydrogen fusion lasts millions of years. Silicon fusion lasts days. The star is racing toward its end, building that iron core layer by layer. And when it explodes, the red supergiant becomes a Type 2p supernova, the P standing for plateau, because the light curve flattens for months as the expanding hydrogen envelope slowly releases its energy. Cool, steady, a long goodbye. Your body releasing energy, slowly, steadily, warmth radiating into the sheets, into the darkness. Wolf-Rayet stars, these are different. They've lost their hydrogen envelopes through powerful stellar winds, mass loss rates of 1/1,000,000th of a solar mass per year. The winds are driven by radiation pressure, photons pushing on atoms, slowly, gradually, eroding the star. What remains is the hot helium core, exposed, blue, luminous, surface temperature 50,000 degrees. These stars explode as Type Ib or Type Ik supernovae. No hydrogen, just helium and heavier elements. The explosions are energetic, brief. Sometimes they produce gamma-ray bursts, jets drilling through the star, emerging into space, beaming energy across the cosmos. Energy radiating outward, while you radiate inward towards center, toward core, toward rest. Luminous blue variables, massive stars that undergo episodic eruptions. They brighten, eject shells of material, then settle, then erupt again. Eta Carinae is the most famous of a binary system, one component as some massive luminous blue variable. In the 1840s it underwent the Great Eruption, becoming the second brightest star in the sky, ejecting 10 solar masses of material. Now we see that material as the homunculus nebula, 2 lobes, dumbbell-shaped, expanding outward. The star has settled, but could erupt again, or could explode as a supernova. We're watching, waiting, learning from each observation. These eruptions might presage the final explosion or might delay it, ejecting mass, reducing the core size, changing the star's fate. Fate is flexible, changeable. Nothing is predetermined, even for stars, even for you. Just drift. Let fate unfold. The mixing in supernova ejector. This is important. The explosion doesn't simply peel off layers like an onion. Instead, instabilities develop. Rayleigh-Taylor instabilities, Richtmeier-Meshkov instabilities, Kelvin-Helmholtz instabilities. The shock wave creates turbulence, mixing, fingers of heavy elements punching through lighter ones. The result is a complex, beautiful structure, knots, filaments, clumps of iron mixed with hydrogen, silicon mixing with helium. This mixing explains why we see heavy elements in the outer parts of remnants. why the composition is more homogeneous than we'd expect from simple spherical layers. The universe prefers complexity, texture, mixing, everything blending together, like consciousness mixing with dreams, boundaries dissolving, elements combining into something new, something soft. Pair instability supernovae, these are theoretical from the very first stars. Population 3 stars, hundreds of solar masses, pure hydrogen and helium, no heavy elements because none existed yet. These massive stars would have developed oxygen cores so hot, so energetic, that photons spontaneously convert to electron-positron pairs. This removes pressure, causes collapse, but then oxygen fusion ignites, explosively. The entire star detonates, completely. No remnant, no black hole, just an expanding cloud of newly created elements, carbon, oxygen, silicon, iron, seeding the pristine universe with the first metals. We haven't definitively observed one, but we've seen candidates, very bright supernovae in distant galaxies when the universe was young, each one potentially a glimpse of these first stellar deaths. First deaths, last deaths. The cycle contains everything, beginning and end united in the explosion and in sleep. The asymmetry of explosions. Most supernovae are not spherical. Observations show, especially from polarization studies, that the ejecta are asymmetric, one-sided, jet-like in some cases. Maybe the progenitor star was rotating. Maybe there was a binary companion. Maybe random turbulence in the collapsing core. This asymmetry can give the neutron star a kick. Conservation of momentum. If more ejecta goes one direction, the neutron star recoils the other way. Some neutron stars are found moving at hundreds of kilometers per second, racing through the galaxy, propelled by their own birth. These high-velocity stars create bow shocks as they plow through the interstellar medium like boats through water, leaving wakes, trails, dim arcs of heated gas visible in X-rays in hydrogen alpha, marking their passage, moving through space, through time, leaving trails of light, of warmth, then darkness again. Magneta flares, some of the most energetic bursts in the universe. A magnetar is a neutron star with an extreme magnetic field, quadrillions of times Earth's. The field is so strong it can crack the neutron star's crust. Starquakes, releasing magnetic energy, sometimes in a giant flare, releasing more energy in 1/10 of a second than the sun emits in 100,000 years. In 2004, we detected one from SGR 1806 just at 20,000 light-years away. The burst temporarily overwhelmed gamma-ray detectors, ionized Earth's upper atmosphere, and was detected bouncing off the moon. Yet it posed no danger. Distance softens everything. Even the most violent events become whispers by the time they reach us. Distance makes everything gentle. Time makes everything soft. Let distance grow between you and waking. Time stretch into eternity. The remnant around the pulsar PSR B15958 appears in X-rays as a ghostly hand, fingers reaching out into space. This is just pareidolia, humans seeing patterns, but it's beautiful nonetheless. The hand is formed by the pulsar's wind, particles accelerating along magnetic field lines, creating jets and toroidal structures. The fingers are just magnetic structures, but they look so organic, so intentional. The universe creates art accidentally, through pure physics. No intention needed, just forces, fields, particles, interacting according to simple rules, creating beauty, complexity, wonder. No intention, just being, just existing, like your breath, in, out. Simple, sufficient. Radioactive decay powers the light curves of supernovae. Initially, the explosion creates nickel-56, an unstable isotope. It decays with a half-life of 6 days into cobalt-56, which then decays with a half-life of 77 days into stable iron-56. Each decay releases gamma rays, which heat the expanding ejector, causing it to glow. This is why supernova light curves have characteristic shapes, brightening as the fireball expands and cools, then declining as the radioactive material decays, following a predictable exponential. By measuring the light curve, we can estimate how much nickel was created, which tells us about the explosion energy, the progenitor mass, the physics of the event. Decay is natural, normal, necessary. Everything bright must fade, must return to darkness, to rest. Some supernovae show hydrogen in their late-time spectra, even type Eq events that shouldn't have hydrogen. This suggests the progenitor had complex structure, maybe shells of hydrogen far from the star, ejected in earlier mass loss episodes. The supernova ejector eventually catch up, collide with this material, lighting it up, revealing it. We call this circumstellar interaction, and it can make supernovae appear brighter, last longer, show unexpected features. The universe is full of these surprises, these complexities, reminding us that our models are simplifications, approximations, useful but incomplete. Incomplete understanding, that's okay. You don't need to understand, just experience, just float. Superluminous supernovae, these are the brightest, 10 to 100 times more luminous than normal supernova. We don't fully understand their power source, maybe interaction with dense circumstellar material, the shock wave converting kinetic energy to light, maybe central engines, magnetars or black holes, powering the display, maybe pair instability explosions from very massive stars. Each explanation fits some events, none fits all. They're rare, occurring in dwarf galaxies, low metallicity environments where massive stars can form. These explosions would have been visible across the universe, beacons shining for months, announcing stellar deaths to any watching civilizations. Beacons in darkness, brief lights, then fading. We're all brief lights, shining, then fading, peaceful. The Tycho supernova remnant from 1572, observed by Tycho Brahe, helped prove that the heavens change, that stars are not eternal and immutable. This was revolutionary. Before then, the The common belief held the celestial realm perfect, unchanging. Only Earth was subject to change and decay. But here was proof, a new star, brightening, fading. The remnant is now a beautiful bubble, visible in X-rays, about 20 light-years across, still expanding. The shock wave has become a cosmic particle accelerator, speeding electrons to nearly light speed, creating synchrotron radiation, teaching us about particle physics, about magnetic fields, about the extreme conditions supernovae create. Proof of change, proof of impermanence, even stars, even you, changing, flowing, temporary, eternal only in cycling, failed supernovae or aborted supernovae. These fascinate astronomers. A star begins to explode, shock forms, starts moving outward, but then falls back. The shock stalls, loses energy, collapses inward. The outer layers fall onto the proton-neutron star, adding mass, until the proto-neutron star collapses into a black hole, swallowing everything. No explosion, no remnant you can see, just a black hole, silently formed. We've caught a few candidates, stars that faded over months, disappeared, leaving nothing. Maybe 20% of massive stars die this way, quietly, without fireworks. Their mass determines their fate, too massive, and they implode rather than explode, sink into darkness rather than blaze into light. Sinking into darkness, that's not failure. That's just another path, another way, equally valid, equally peaceful. Circumstellar disks around supernova progenitors. Some massive stars have these. Material in orbit, like planetary systems, but closer, hotter, more massive. When the supernova occurs, the shock wave hits this disk, creating asymmetric light, polarization, complex structures. The disk might be from a binary companion or from the star's own equatorial mass loss. Either way, it affects what we see, how the light curves evolve, the spectral features, adding another layer of complexity, another variable, another piece of the puzzle to understand. Layers upon layers, complexity upon complexity, but underneath, simplicity, rest, emptiness. Just allow. Often afterglows. These are puzzling. We detect gamma-ray burst afterglows, the fading emission after the initial burst, but without the burst itself. Either we missed the burst, looking the wrong direction, or it was beamed away from us, only the afterglow visible from our angle. These orphans teach us about beaming, about geometry, about how many bursts we're missing. For every burst we see pointing toward us, there might be 100 pointing elsewhere, their afterglows visible, their main event hidden. The universe is full of things we almost see, almost detect, almost, but not quite, almost awake, almost asleep, drifting in the space between, comfortable, soft, neither here nor there. Reverse shocks in supernova remnants. When the expanding ejector encounter dense material, the shock doesn't just heat the material, it bounces back, creating a reverse shock, propagating backward through the ejector. This heats the ejector from behind, creating different emission, different structures. In Cassiopeia A, we see this beautifully. X-ray emission from both forward and reverse shocks, each heating different material, revealing different elements. Silicon in the reverse shock, hydrogen in the forward shock. The structure is complex, layered, beautiful, like looking at geology, but in space, in motion, frozen by distance into apparent stillness. Layers of consciousness, surface thoughts, deeper feelings, deepest rest, all layered, all present, all settling. Quark novae. These are hypothetical, even more exotic than supernovae. The idea is that a neutron star, under extreme conditions, might undergo a phase transition, neutrons breaking down into quarks, creating quark matter. This releases energy, maybe enough to create a second explosion. Days after the initial supernova, a double-peaked light curve. We've seen candidates, supernovae that brighten, fade, then brighten again. Could be quark novae, could be circumstellar interaction, could be something else. The universe keeps surprising us, suggesting new physics, new states of matter, new possibilities opening, even in ending, even in death, even in sleep. Transformation, not termination. Light echoes from historical supernovae. We can still study them. Centuries later, the light from the explosion travels outward, but some goes in other directions, hits dust clouds, reflects toward us, arriving years or centuries after the direct light. By finding these echoes, we can take spectra, classify the explosion, measure velocities, study supernovae that occurred before we had the tools to observe them properly. The Tycho supernova, Kepler's supernova, even the Crab. We've found light echoes from all of them, ghostly reflections, allowing us to reconstruct history, to see what those astronomers saw, but with modern instruments, modern understanding. Echoes of the past, still reverberating, still teaching. History isn't gone, just quiet, distant, faded. Population 3 supernovae from the first stars. These would have been different. No metals, pure hydrogen and helium. Stars could grow more massive, hundreds of solar masses. They would burn hot, fast, die young. Their supernova might have been pair instability events, complete disruption, or they might have collapsed directly to black holes. Either way, they seeded the universe with the first heavy elements: carbon, oxygen, silicon, iron, creating the conditions for later generations, for planets, for life. We're searching for them in the most distant galaxies, the earliest epochs, looking for their distinctive signatures. So far, maybe candidates. Nothing certain. They remain theoretical, imagined, ghostly, theoretical, imagined, like the boundary between thought and dream. Is there a difference? Does it matter? Strange stars, another exotic possibility. Maybe quark matter is more stable than neutron matter. If so, Neutron stars might be metastable, eventually converting to strange stars made of up, down, and strange quarks. This conversion might release energy or absorb it, might be sudden or gradual. We don't know. We've looked for strange star candidates, pulsars with unusual properties, but nothing definitive. They might not exist, or might be common but indistinguishable from neutron stars. Another mystery, another gap in our knowledge. The universe keeps its secrets, reveals them slowly, or not at all. Secrets are okay, not knowing is okay. Mystery is where peace lives, in the unknown, the unknowable. Accretion-induced collapse, a different path to neutron stars. Start with a white dwarf, accreting material from a companion, slowly, steadily, approaching the Chandrasekhar limit. Normally it would explode as a type Ia, but if conditions are right, if accretion is slow enough, the white dwarf might collapse instead. The oxygen-neon-magnesium core overcome by gravity, collapsing directly to a neutron star. This produces a faint supernova, or maybe no visible explosion, just a sudden transition. White dwarf to neutron star, a quiet death, a secret transformation. We think this happens, but it's rare, or well hidden, or both. Quiet transformations, from one state to another, no drama needed, just change, inevitable, natural. Common envelope evolution. This affects binary star systems. When one star expands to red giant, it might engulf its companion. Both stars orbit inside the giant's envelope. Friction, drag. The orbit spirals inward, tightens. Meanwhile, the envelope expands, ejected by the orbital energy. Eventually, you're left with a tight binary. Both cores close together. This sets up future interactions, mass transfer, mergers. It affects the final supernova, whether it happens, how bright it is, what it leaves behind. Binary evolution is complex, messy, difficult to model, but critical. Most massive stars are in binaries, their lives and deaths intertwined, connected, even in death. Nothing is truly alone. Everything touches, everything affects. But right now, you're allowed to be alone, separate, at peace. Hidden supernovae, a rare subclass, showing strong helium emission. They occur in or near starbursts, regions of intense star formation. The progenitors are massive, perhaps in interacting binaries. The explosions are bright but fade quickly. Their helium-rich spectra suggest unusual progenitor winds or circumstellar material. They're not well understood. Too few examples, each one adding data. Each detection refines our categories, suggests new progenitor channels. The taxonomy of stellar death is complex, growing more detailed, more nuanced with every discovery. Categories dissolving, boundaries blurring. Everything flows into everything else. Supernovae into remnants, remnants into space, space into stars, stars back to supernovae. Endless, cycling, eternal. R process elements, the rapid neutron capture process. This creates elements heavier than iron, gold, platinum, thorium, uranium. It requires extreme neutron density, billions of times normal. This happens in supernovae, especially in the neutrino-driven winds, and in kilonovae, neutron star mergers. The freed neutrons attach to seed nuclei faster than they can beta decay, building heavier, creating elements that don't exist naturally on Earth anymore, only in trace amounts from ancient supernova dust that formed the solar system, the gold in jewelry, platinum in electronics, all made in these violent events, then cooled, condensed, incorporated into planets, into us. You are made of violence transformed to peace, explosion cooled to stillness, energy become matter, become life, become consciousness, become sleep. Infrared echoes from dust cocoons. Some supernovae are obscured by dust, thick clouds surrounding the progenitor, absorbed optical light, but the dust heats up, glows in infrared. We see the supernova indirectly through this warm glow. The light curve is different, smooth, prolonged. The dust radiates for months, years, slowly cooling. This tells us about mass loss in the years before explosion, about the circumstellar environment, about what the star was doing in its final millennium. Indirect light, reflected warmth. You don't always see things directly. Sometimes you sense them, feel them, know them without seeing, like sleep approaching. You don't see it, you feel it, coming, closer. Molecular cooling in supernova ejecta. Years after the explosion, the gas cools enough for molecules to form: carbon monoxide, silicon oxide, even dust grains. This molecule formation releases energy, infrared light. We can detect this, measure it, understand the chemical evolution of the ejecta, how atoms combine, how complexity emerges from simplicity. In Supernova 1987A, we detected molecules, watching them form in real time, watching the ejecta cool, transition from plasma to gas to molecules, to solid dust grains, the full cycle of matter, from star to space to solid, from energy to matter, from motion to stillness, from thought to sleep, the natural progression, unavoidable. Welcome. Photoionized filaments in old remnants. Thousands of years after the explosion, the remnant is large, is faint, diffuse, but near hot stars, the filaments light up, ionized by starlight. We see them in hydrogen alpha, glowing red, delicate, wispy, barely there. These trace the old supernova shell, show us where it's gone, how it's dispersed, the oxygen, the neon, the sulfur, all mixed now with interstellar gas, indistinguishable except in these faint glowing regions. The supernova is nearly gone, nearly dissolved, becoming part of the general medium, its identity fading, merging with everything, identity fading, individuality dissolving, becoming part of everything. No separation, no boundary, just being, just existence, simple, perfect, bow shocks from runaway stars. When the progenitor star was ejected, or when the neutron star received a kick, they can reach high velocities, hundreds of kilometers per second. As they plow through space, they create bow shocks, compressed gas glowing in infrared, in optical, arcing ahead of the star like wake of a boat. These bow shocks are beautiful, asymmetric, shaped by the star's motion and the density variations in the medium, each one unique, each one a record of a violent birth, a kick received, momentum conserved, energy dissipating over millennia, moving through resistance, creating patterns, leaving beauty behind, then moving on, just motion, just time, just change. Pre-explosion eruptions. Some massive stars undergo eruptions in the years before they explode. Luminous blue variables, yellow hypergiants. These eruptions eject shells of material, solar masses worth, creating dense circumstellar environments. When the final supernova occurs, its shockwave crashes into these shells, creating bright, long-lasting displays, superluminous events. The 2006 supernova SN 2006G, one of the brightest ever, showed signs of this interaction. The progenitor had shed huge amounts of mass decades earlier. Those shells, called the supernova ejector, converted kinetic energy to light, blazing across the cosmos. Preparation. Even stars prepare, shedding what's unnecessary, lightening, simplifying, before the final transformation. What can you shed? What can you release to prepare for rest? Pair instability pulses before the final pair instability supernova. A very massive star might undergo pulses. The core briefly goes pair instable, explodes, but not enough to disrupt the star. It ejects shells, then settles. The core rebuilds. Later, another pulse, another shell. This can repeat, creating multiple shells, onion-like structure around the star. The final explosion, when it comes, interacts with all these shells, creating a complex light curve, multiple peaks, prolonged emission. We've seen candidates. Supernova IPTF 14HLS brightened and faded repeatedly over years. Maybe pair instability pulses, maybe something else. The universe is more creative than we imagined. Pulses of consciousness, brightness, then dimming, then brightness again, until finally, continuous dim peace, restful, complete. Silicon layers in young remnants, freshly ejected from the explosion. Silicon is visible in X-rays, emission lines at specific energies. Over time, as the remnant expands and cools, these lines fade. The silicon disperses, mixes, becomes harder to detect. But in young remnants like Cas-A, Tycho, Kepler, we see beautiful silicon structures, knots, filaments, jets. These trace the explosion geometry, show us asymmetries, teach us about mixing, about the complex three-dimensional structure of the blast. Each remnant slightly different, each one a frozen moment, a snapshot of violence becoming peace, structure dissolving into smoothness, detail fading to simplicity, complexity relaxing to uniformity. This is the natural way, the peaceful way, the way of all things. Magnetic towers in remnants. The magnetic field can create tall structures, loop-like, towering above the remnant. Plasma follows field lines, spiraling, glowing. These towers are visible in radio, in X-rays, marking where magnetic energy dominates, where fields are strongest. They tell us about the progenitor's magnetic field, about dynamos in the collapse, about how magnetic energy is distributed and dissipated. Beautiful structures, invisible to the eye, but real, powerful, slowly fading as the field weakens over millennia. Invisible structures supporting visible reality, like the scaffolding of consciousness supporting thoughts, mostly hidden, mostly unfelt, but there, slowly, relaxing. Cobalt decay in late-time light curves. After nickel-56 decays to cobalt-56, the cobalt takes over. 77-day half-life, slower. The light curve follows this decay, exponentially declining, smooth, predictable. By measuring the decline rate, we confirm cobalt, confirm our understanding of nuclear physics, of radioactive decay. The curve can last for years, gradually fading, until the supernova becomes too faint to detect, lost in the noise, the background, but it's still there, still expanding, still glowing, just too dim for us to see. Our limits, not the universe's, too dim to see, too quiet to hear, but still existing, still real, like the edge of sleep. You can't quite perceive it, but you know it's there, coming, arriving, now. Anomalous X-ray pulsars. These might be magnetars, or might be something else. They pulse in X-rays, periods of seconds to minutes. They spin down rapidly, losing energy. Their magnetic fields must be extreme to explain the energy loss. But they're not typical pulsars. They behave differently, emit differently. They might be young magnetars, or neutron stars with fallback disks, or something exotic. Each discovery raises questions, suggests possibilities. The universe has more types of objects than we have names for, more physics than we've discovered. We're still exploring, still learning, still surprised, still learning, even at the edge of sleep, even in dreams. The mind processes, understands, integrates, but you don't need to try. Just allow, just receive, just rest. Strontium filaments in supernova remnants, recently detected, glowing in optical light. Strontium atoms excited by the reverse shock. This is exotic, rare, beautiful. Strontium is an S-process element, usually made in asymptotic giant branch stars, but we see it in supernova remnants too, perhaps made differently, perhaps transported. Each discovery opens questions. Do we understand nuclear synthesis? Do we know all the ways elements form? The universe keeps teaching, keeps revealing, keeps surprising us with its richness, its complexity, its beauty. Richness in simplicity, complexity in rest, beauty in darkness. The universe holds everything, including you, including this moment, this breath, this letting go. Neutrino-driven winds from proto-neutron stars. In the seconds after core bounce, the proto-neutron star is incredibly hot, 1 trillion degrees. It cools by emitting neutrinos. Those neutrinos deposit energy in the layers above, driving a wind, This wind can be neutron-rich or proton-rich. Depending on conditions, it might create our process elements, gold, platinum, or lighter elements. These winds are complex, multidimensional, turbulent. We simulate them on supercomputers, trying to understand, trying to predict what elements form, how much, where do they go. Slowly, we're learning. One simulation, one observation, one comparison at a time, learning slowly, understanding gradually, like sleep arriving, not sudden, not forced, just gradually, naturally, unavoidably, scattered light from pre-explosion eruptions, years before some stars explode. They brighten, erupt, eject mass. This creates shells of dust, far from the star. When the supernova occurs, its light travels outward, hits these distant shells, scatters. Some scatters toward us, arriving months or years late. We see light echoes, bright rings expanding around the supernova position, like ripples on a pond, but in light, in time. These echoes let us study the eruption that occurred before, understand the progenitor's final years, map the dust distribution. Beautiful, informative, unexpected, echoes, reflections, light returning after traveling, like memories surfacing, then fading, then dissolving into sleep, into peace, into nothing. Turbulence in post-supernova clouds. The remnant creates turbulence in the interstellar medium, swirling, mixing. This turbulence can persist for millions of years, long after the remnant itself is gone. It stirs the gas, creates density variations, triggers instabilities. Some of this turbulence might trigger star formation or might inhibit it. We're still learning, still measuring. Turbulence is hard, chaotic, difficult to model, but it's important. It affects everything. How gas moves, how stars form, how galaxies evolve. The legacy of supernovae extends far, far beyond their visible remnants. Influence extending, affecting everything, long after the source is gone, like thoughts influencing dreams, consciousness fading but affecting what comes after, continuity in change, the scatter of interstellar metals. Every supernova adds metals to space, iron, oxygen, carbon, silicon. These mix with the interstellar gas, enriching it. Over billions of years, generation after generation of stars, the metallicity increases. The first stars had none. The sun has about 2%. Future stars will have more. This gradual enrichment enables rocky planets, enables life, enables us. We are the universe becoming aware of itself, made possible by countless supernovae, billions of explosions, each contributing atoms, until finally enough complexity, enough chemistry for life, for thought, for consciousness, for sleep, for rest, for peace. The universe created conditions for you to exist and to rest right now. Rest is what you do. Rest is your purpose, your only task. Just rest, just sleep. The universe keeps turning, Supernova explosions echo softly across the void and will keep drifting, floating together through the mysteries. 100 supernova explosions mysteries are looping softly to endlessly through the night. The stars burn quietly, fuse elements patiently, approach their ends inevitably. Some explode, some collapse, some fade, all return, their matter recycled, their energy dissipated, their patterns dissolved, but not gone, never gone, just changed, transformed, continued, and we drift with them through the mysteries, through the darkness, through the soft and endless night, heavier, heavier, sinking, floating, breathing with the rhythm of space itself. Thump, thump, your heartbeat slowing, matching the pulse of distant stars. The mattress holds you, gravity embraces you, darkness surrounds you, and somewhere, far away, a star collapses, a core bounces, neutrinos flood outward, light begins its journey, across space, across time, to eyes that may never see it. But that's okay. Not everything needs to be seen. Some things just exist, in the dark, in the quiet, in the peace, like you, right now, existing, resting, sleeping, drifting through 100 mysteries as through infinite space, through the gentle, endless night.